From this video, we will start next chapter from physics, that is oscillation. In basic concept, first you should know what is meant by periodic motion. Then what is vibratory motion or oscillatory motion. In this chapter, oscillations, we are going to study a special oscillatory motion, a special vibratory motion called linear simple harmonic motion. There is a detailed study of linear simple harmonic motion in this chapter. First, I will explain here what is meant by periodic motion. What is periodic motion? In everyday life, we come across many examples of periodic motion. One example is motion of hands of a clock. Motion of hands of a clock is a periodic motion. Revolution of planet around the sun is also example of periodic motion. What is periodic motion? Any motion which is repeated, any motion which repeats itself after particular interval of time is called periodic motion. In clock, you will find that the motion of hands, whether it is minute hand, hour hand or second hand, is get repeated after a particular interval of time. Therefore, it is a periodic motion. Revolution of earth around the sun is also periodic motion. Same motion is repeated after particular interval of time, that is after 365 days. This is periodic motion means what? Remember that in periodic motion, every position of the particle or body is repeated after particular interval of time. Or you can say that set of moments of that body or particle is repeated after particular interval of time. In periodic motion, there is the repetition of set of movements of particle or body after some particular interval of time. The time taken by set of movements shown by the body or particle is called period of that motion. Time taken by set of movement shown by the particle or body is called period of that motion. This is periodic motion means what? Generally, period of any periodic motion we denote by letter capital T, and we always measure this period in seconds. Period is always measured in seconds. After this periodic motion, we will see what is meant by vibratory motion or oscillatory motion. Vibratory motion or oscillatory motion. What is vibratory motion? A motion in which body or particle move to and fro about its mean position. Move to and fro about its mean position periodically. That motion is oscillatory motion or vibratory motion. You can define this vibratory motion in another way also. A motion in which a body or particle moves back and forth about its mean position. It is also called vibratory motion or oscillatory motion. Vibratory motion or oscillatory motion. Some examples of vibratory motion and oscillatory motions are: take simple pendulum. This is simple pendulum. This is called bob of simple pendulum. If we disturb the bob of the simple pendulum from its rest position, then we observe that this bob, it moves to and fro about its rest position, which is called mean position. It moves to and fro about its rest position called mean position. This type of motion is a vibratory motion or oscillatory motion. Second example, you may take tuning fork. This is the tuning fork. These are the prongs of tuning fork. When we set this tuning fork in vibration, when we set this tuning fork in vibration, observe the motion performed by the prongs of this tuning fork. These prongs of tuning fork, you will find that they move to and fro about their rest position called mean position. Rest position is always mean position. When we hammer this tuning fork on some rubber band, the prongs of tuning fork will perform vibratory motion. The prongs will vibrate to and fro about their mean position. This is also called vibratory motion or oscillatory motion. Next example. Suppose this is smooth surface. On this smooth surface, one rigid block is taken, which is attached to one end of the spring, and another end of the spring is attached to the wall. To the one end of the spring, block is attached. Another end of the spring is fixed to the wall. Now, if we stretch this block towards right side and then release, this is its mean position. This is its rest position. Now we stretch that block towards right side and then release. What happens here? You will find that this rigid block moves back and forth or to and fro about its mean position. This rigid block, it moves to and fro about its mean position. When we release this block by stretching it towards right side. This will be the motion shown by the block. This will be the motion shown by the block when we release it by stretching towards the right side. This is its mean position, rest position. Now we have stretched these blocks towards right side. This is maximum limit up to which we have stretched that block. And now after that we have released that block. Here we observe that this block, it moves to and fro motion on this smooth surface. This is its extreme position towards left side of equilibrium position, towards left side of rest position. This is also vibratory motion or oscillatory motion. These are the examples of vibratory motion or oscillatory motion. Remember that every oscillatory motion is a periodic motion. However, every periodic motion is not oscillatory motion. Uniform circular motion is a periodic motion, but it is not oscillatory motion. Every oscillatory motion is periodic, but every periodic motion need not be oscillatory. Now, after this, in this chapter, we are going to see simple oscillatory motion called linear simple harmonic motion. Simple oscillatory motion called linear simple harmonic motion. Why there is the word linear? Remember that we have two types of oscillatory motion. Some oscillatory motions are linear, while some oscillatory motions are angular. If the oscillatory motion shown by the body is along the straight line, then that is linear oscillatory motion. And if the oscillatory motion shown by the body is along the arc of the circle, then it is angular oscillatory motion. Here, first we are going to see in detail a simple oscillatory motion called linear simple harmonic motion. Linear simple harmonic motion, short form is SHM. What is this linear simple harmonic motion? Linear simple, harmonic motion. Short form is SHM. Short form is SHM. SHM. Linear SHM. First, we will see the definition of this linear SHM. Which oscillatory motion is called linear SHM. Then after that, mathematical explanation. And then we will find differential equation. We will find differential equation for linear SHM. First, definition. Definition. To understand this definition, consider an oscillatory motion, vibratory motion along the path AOB. Suppose that there is one particle. There is one particle performing vibratory motion along this path AOB with O as the mean position, with O as the rest position. When particle is at its rest position, suppose particle is here, the displacement of that particle comes equal to 0. When particle is at rest position, we say that the displacement shown by the particle is 0. Suppose that after some time interval, particle reaches up to this point P. After some time interval, the particle reaches at point P. The displacement shown by the particle, consider equal to S. This displacement is always measured from mean position. Displacement is always measured from mean position. At some instant, we have considered that particle is at point P and its displacement is X. Displacement is always measured from mean position. Here mean position is point O. Particle is performing oscillatory motion along this path AOB. See, how is the path? The path is linear. It is oscillatory motion, means it must be periodic. Linear and periodic. In this motion, which is linear, oscillatory, means periodic, we find that always force acts on that particle. Always force acts on that particle. The force is called restoring force. This force which acts on the particle performing vibratory motion along this path, it is called restoring force. Why it is called restoring force? This force always tries to restore the position of that particle. This force always tries to restore the position of that particle. Means anywhere along this path, we find that the force acting on the particle is always directed towards the mean position of that particle. Anywhere along this path, we find that the force, restoring force, is always directed towards the mean position of that particle. Particle is here at some instant. If we observe the restoring force acting on the particle, you'll find that this force acts in this direction. In this direction means towards mean position. Displacement is towards right side. Force is directed towards mean position means towards left side. So that the displacement shown by the particle is towards left side. Then here the direction of force will come towards right side. If the displacement shown by the particle is towards left side, the direction of restoring force will come towards right side because mean position lies on right side. The force is always directed towards mean position. How is the restoring force in this type of motion? It is always directed towards mean position. Or it is in the opposite direction of displacement. It is in the opposite direction of displacement. Beside this means beside the direction of force, you will find that the magnitude of that force, magnitude of this restoring force, it is proportional to displacement of that particle from mean position. Magnitude of that force, you will find that it is proportional to displacement of that particle from mean position. If particle shows greater displacement, then of course greater restoring force will act on that particle. If the particle reaches to this extreme position, of course the magnitude of restoring force acting on the particle will be greatest. Such a linear, periodic, vibratory motion in which the restoring force acting on the particle is always in the opposite direction of displacement and is proportional to displacement of that particle from mean position is called linear simple harmonic motion. Definition: a linear, periodic, vibratory motion in which the restoring force acting on the particle is always directed in the opposite direction of displacement and whose magnitude is proportional to displacement of the particle from mean position is called linear simple harmonic motion. In linear simple harmonic motion, two conditions are required. One is the direction of restoring force must be opposite to that of displacement. And second is, this force must be proportional to displacement. Any motion which satisfies these two conditions will be the linear simple harmonic motion. Now, we will explain this mathematically. This F is a restoring force. In SHM, we are saying that this restoring force is always proportional to displacement. So that X is the displacement of particle from main position. Then write F proportional to X. The direction of force is always opposite to displacement. Therefore, write here minus sign also. In linear SHM, you will get F proportional to minus of X. Remove proportionality sign by putting constant K. Remove proportionality sign by putting constant K. You get F equal to minus K. F equal to minus K. This K is called force constant. This K is called force constant. How we can define this K? To define this K, take this equation in magnitude. In magnitude, you get restoring force how much? K into X. Negative sign indicates always direction. In magnitude, F you get K into X. From this we get K, which is force constant, F by X. Force constant is given by F by X. This is the mathematical form of force constant. Of course, unit for this force constant will come Newton per meter. And you can find dimensions also. Dimensions for force are M1, L1, T minus 2. Dimensions for displacement L1. L1 will get cancelled. You'll get dimensions for force constant M1, L0, T minus 2. Definition you can write from this mathematical form. Force constant of linear SHM. Force constant of linear SHM is defined as the magnitude of restoring force. Magnitude of restoring force acting on the particle when its displacement from mean position is equal to 1 unit. When the displacement of the particle from mean position is equal to 1 unit, whatever is the restoring force acting on that particle, it is nothing but force constant of that linear simple harmonic motion. This is the definition of force constant. Remember that in linear SHM, mathematically we can write F equal to minus K. K is called force constant. In magnitude, you will get F equal to Kx. You know that force is always mass into acceleration. Therefore, this equation can be written as m into a equal to minus kx. From this we can write acceleration. From this we can write acceleration. How much? Minus k by m times x. Remember that. If force is always in opposite direction of displacement, then acceleration also comes in the opposite direction of displacement. There is a negative sign, see. Because force is nothing but mass into acceleration. Any motion in which you will find acceleration is in the opposite direction of displacement and is also proportional to displacement, that motion is nothing but linear SHM. That motion is nothing but linear SHM. This is the definition of linear SHM. Now after this, we will find differential equation for linear SHM. Differential equation for linear SHM. Differential equation for linear SHM. Generally, question is asked on this for 2 marks in board exam. See how to find this differential equation. What is the differential equation? An equation in which derivative is present is called differential equation. That derivative may be first order derivative, second order derivative, third order derivative, or any order derivative. What is the differential equation for linear SHM? For linear SHM, we have seen that. For linear SHM, we have seen that the restoring force acting on the particle is always minus k into x. F is always minus k into x, where k is a force constant. Where k is what? Force constant. Now, by second law means by Newton's second law, this force we can write mass into acceleration. M is mass of that particle which is performing linear SHM. Mass into acceleration gives us force acting on the particle by Newton's second law. Therefore, we get m into a equal to minus kh. A means acceleration. A means acceleration. You get acceleration here minus k by m into x. Acceleration is minus k by m into x. This acceleration, it is a rate of change of velocity with respect to time. It is a rate of change of velocity with respect to time, dv by dt. Here, there is a derivative. Therefore, this is a differential equation. But in this differential equation, there are 3 variables. One is v, which is nothing but velocity. Second is x, which is nothing but displacement. And third one is t, time. We want such a differential equation in which there are only two variables. To convert this into variables, use the definition of velocity. Velocity is nothing but rate of change of displacement with respect to time. Replacing v by dx by dt. You get here d dt of dx by dt equal to minus k by m into x. D dt of dx by dt. There is the derivative of derivative. When we take derivative of derivative, it becomes second order derivative. This is second order derivative of displacement with respect to time. Write it like this: d2x upon dt square. d2x upon dt square is equal to minus k by m into x. Minus k by m into x. This k by m, it comes equal to this k by m, it comes equal to omega square. Omega means angular speed. In next part of this chapter, we will see this, how k by m comes equal to omega square. Omega is the angular speed. Replace this k by m by omega square. We get d2x upon dt square equal to minus omega square x, or d2x upon dt square plus omega square x equal to 0. Here there are two variables. One is x, second is t. One is displacement and second one is time. This is the differential equation of linear SHM. d2x upon dt square plus omega square x equal to 0. Any motion which satisfies this differential equation will represent linear, simple, harmonic motion. This is all about differential equation of linear SHM. Next part of this chapter I will explain in next video.